Hello, and welcome to this webinar on structural and thermal analysis with MATLAB. My name is Sergio Obando, and I'm an application engineer at MathWorks. The goal for this presentation is to show you how you can easily set up your FEA or finite element analysis simulations and leverage the MATLAB environment to solve problems typically encountered by engineers and scientists in a variety of fields such as aerospace, automotive, and energy. Before we get started, let me first show you a preview of some of the items we will be developing today. Using a few lines of code, we will see how you can analyze the behavior of mechanical components under different physical effects. In this PDF report, we show a thermal analysis of a robot arm component. In this report, you will find temperature distributions, figures, code, and test results for multiple materials. This report could be shared with our colleagues to summarize all relevant information and present results. Another item that we will cover today is how to create custom applications for our FEA models. This app shows the solution of a stress analysis of a bracket and can be easily deployed and used in the field even by non-technical people. If this sounds of interest to you, stick around and see how you can implement these solutions to your own FEA applications. With that in mind, here's the agenda for today. We will start with some basic overview and motivation for finite element analysis and cover the workflow using 3 application examples. Lastly, we will share some resources to find more information on the subject. So what is the goal of structural and thermal analysis? These models allow us to understand and assess the response of components under loading, vibration, or heat, and determine deformation stresses among many things. And thus, for example, select the best material and even prevent failure or undesired resonance. These systems are typically modeled using partial differential equations or PDEs that capture the underlying physics of the problem, and FEA is just one of the most common methodologies to solve this type of equations. You don't have to be an expert to solve these PDEs. MATLAB and the PDE toolbox makes it easy to set up and analyze PDEs in applications such as heat transfer, static deflection, modal analysis, as well as structural dynamics and custom PDEs. Let me show you how to solve a problem in 10 lines of code. Let's go to MATLAB. I'm going to be using a live script to edit and execute my code. If you're not familiar with the live editor, it's an interactive environment for exploratory programming that offers rich formatted text, equations, and images so that you can create a narrative of your problem. For instance, I may want to insert a title here. So this is going to be heat transfer in 10 lines. Add some additional information. And for instance, insert an image so that people know what my code is about. The PDE workflow typically involves the following 3 steps. First, create or load a geometry and generate a mesh. Second, determine the type of model and boundary and initial conditions of the system. Third, find the solution of the FEA and visualize and post-process the results. Let's start with the first step. Consider heat transfer or conduction in a pipe. I'm going to create a simple geometry using a parameterized shape of a cylinder using the command multi-cylinder. All right, so first, just create a model. Tell MATLAB using the create PDE function. This is going to be a thermal model. And again, create a geometry by using multi-cylinder. There are other shapes that you can use depending on your model, such as spheres and cubes. I'll define 3 layers, one of radius 20, 25, and 35, a height of 20. And I'm going to remove the material at the center or make it a hollow cylinder by telling MATLAB to remove the cylinder of radius 20. Now that I have a geometry, I'm going to assign that geometry to the model that we've defined. I'm not sure if you've noticed so far, but the live editor is providing some contextual hints to help me with the syntax of my code. If at any point I have any questions about any of these functions, I can always rely on the documentation by searching the particular function that I have questions about. All right, so I've assigned a geometry to my model. And now that I've assigned that geometry, I want to visualize it to make sure that I created the correct geometry. So using the function pdgplot, I pass my model and I execute the code. As you can see, I have a multi-layer cylinder. Actually, to make it a little easier, I'm going to pass an additional argument to have all the face labels turned on. All right, let's execute one more time. All right, as you can see, the inside face is phase 3, the outside face is phase 7, which is going to come handy when we start defining the boundary conditions of the problem. All right, so created or defined the PDE, created a geometry. Now let's generate a mesh. So we use the generate mesh function, passing our model to it. And then let's visualize that mesh using the function PDE mesh. All right. So using the lab editor, I've defined my geometry and the type of problem, mesh.geometry, using this interactive environment. All right. So now I can pass to step 2, which is apply material properties and boundary conditions. So these are the parameters that govern the physics of the problem. So in terms of thermal properties, the outer layer of this pipe is going to have low thermal conductivity, meaning it's going to be acting as an insulator, while the inner ring will have a larger heat transfer portion to it, so a larger or a bigger thermal conductivity value. All right, so I use the thermal property function. I pass my model, and I'm going to use cell 1, which is the inner ring or the inside of the pipe. And in terms of the material property, I'm going to assign a thermal conductivity of 40. All right, expand this a little bit. For the outside ring, I'm going to use a similar setup. So thermal property of my model, cell 2, and thermal conductivity of 0.15. All right, so those are the material properties of my system. Now for boundary conditions, I use the function thermal BC or thermal boundary condition model, and I'm going to assign to the inside phase, which we saw was phase 3, a constant temperature of 85 degrees. As you can see, there are some additional options there so that you can model using the right boundary conditions of your problem. Thermal BC, model, phase 7, which is the outside phase. And I'm also going to define temperature to be 4 degrees. So to summarize what we've done so far, we defined the geometry, defined thermal properties and boundary conditions, and now to move on to step 3 to solve the problem. So I'm going to say that results is equal to solve, and I pass the model. So part of step 3 is also to visualize or post-process those results. So I use the function pdplot3d of my model, and I define the colors of that geometry or that deformed shape to be based on my results. And I want to use, let's see, the temperature. All right, let's execute this one more time. All right, so as you can see, we have the solution to our problem. So the thermal analysis of a hollow cylinder where the inside face is held to a constant temperature and the outside face is also held to a constant temperature. As you can see, with 10 lines of code, I can go through the typical FEA workflow using domain-specific terms with meaningful function names and arguments to solve my problem. The Partial Differential Equations Toolbox provides this and many more capabilities to help you get started with finite element analysis. These three steps that we just showed have been part of a multi-year effort to simplify and improve the PDE workflow in MATLAB. So if you have not used the PDE Toolbox in a while, or you're new to it, please visit our website and the documentation for more information. Another great thing about this workflow is that you can easily extend your analysis by leveraging the MATLAB environment. Let's see some application-specific examples to see these extensions, such as performing parameter sweeps in parallel, generating reports, and standalone executables. If you remember at the beginning of the presentation, I showed a report of a U-bot robot arm. The objective of that analysis was to determine the heat tolerance of that component and to model the relationship of thermal conductivity and max temperature to avoid undesired performance of the robotic arm. Let's see how to perform this analysis using MATLAB and the PDE toolbox. The part under analysis is this gripper pivot, which is part of a U-bot robotic arm. This pivot is exposed to heat through conduction of heat generated by a circuit board placed on top of it. Let's see the PDE workflow for this specific application. Again, we define the type of model we're solving, in this case a thermal steady state problem. We're going to import our geometry using an STL file, which can be generated through most CAD packages. Then we use the PDE plot function to visualize the geometry. So this is the geometry we've imported. The next step is we need to generate a mesh. Now to generate a mesh, we need to know what the dimensions are of this geometry so that we can choose or decide on the appropriate element size for the tetrahedrons. Now, the dimensions that were supplied by the manufacturer show us that this gripper pivot is about 32 millimeters. Now, if you look at the geometry, it seems that it's probably dimensioned in inches. So we're going to have to figure this out to make sure that we're using consistent units. Let's generate a mesh using a maximum element size for the mesh of 0.09 inches. And then we're going to visualize that mesh using the PDE mesh function. All right, so this is the result of the mesh that we've generated for this part. And again, just to verify that we're using the proper dimensions, we can use the information from the generated mesh to determine the maximum length of all dimensions of our part. In this case, we determined that the part is about 1.46 inches, which is close to what the manufacturer specification was determined. Step 2 in our PDE workflow is to set up the material properties and boundary conditions. So we're going to assume that the material is a magnesium alloy with a thermal conductivity of 52 watts per meter Kelvin. Now, if you remember, the units of our part are given in inches, so we are going to use the symbolic math toolbox to easily change from 52 watt per meter Kelvin to watts inch Kelvin. So this is fairly simple. We use U sim unit, give the expression in watts meter Kelvin, and then just have MATLAB rewrite it to an expression in terms of watt inches Kelvin. So this thermal conductivity in inches is 1.32. So we use, again, thermal properties of our thermal model with a thermal conductivity of 1.32. All right, in terms of boundary conditions, we're going to assume that all the sides of the gripper pivot are going to be exposed to the air temperature, so having a natural convection of 25 watts per meter square Kelvin. And the ambient temperature in Kelvin is 288.15 Kelvin. Again, we have to keep consistent units, so we're going to change this watt meter square Kelvin to watt inch square Kelvin. Okay, so again, thermal boundary condition, thermal BC of our thermal model, and the phases that are external to the part exposed to a convection coefficient of watt inches square Kelvin, to an ambient temperature of 288.15. Now the bottom part of the component is going to be attached to the robotic arm. So we're going to assume that is being held to a constant temperature, while this inner circle and the top face, which is closest to the circuit board, is going to have some heat flux. So thermal boundary condition, thermal model, phase 43, which is the lower power, is going to be held to a constant temperature, meaning the robotic arms is acting as a heat sink. And the top face and the inner hull are going to be exposed to a heat flux of 25 and 10. All right, so we've gone through step 1 and 2 of our PD workflow. Let's move on to step 3, which is solving and post-processing the results. Okay, so to find the solution, we use the command solve, pass the thermal model that we've created, and store the results in a variable called results. I'm also using tick and talk, which is essentially a timer, to measure how long it takes to solve a single version of this problem. Now this should take about 20 seconds or so. And now that we have those results, let's post-process them. So the first thing that we're going to do is we're going to rewrite those max temperature results from Kelvin to a more common unit such as Celsius or Fahrenheit. Again, I'm taking advantage of the symbolic math toolbox to do a lot of the rewriting here. So the max temperature of the part is 312 Kelvin, which is about 39 Celsius or 103 Fahrenheit. I also like to visualize, so again, I use the PD plot 3D of the thermal model, and I use the color map data argument to visualize the temperature results of the part. So this allows me to see how the temperature distribution on the bulk of the part is being transmitted. So again, the largest temperature is on the part that is closest to the circuit board, and then as the heat moves along the part, it gets dissipated. Next, I'd like to extend this analysis to perform a design of experiments and parameter sweep to determine both the best material selection and to find the relationship between thermal conductivity and max temperature. So the way I'm going to do that is by bringing in additional materials. So I have 5 additional thermal conductivities representing 5 additional materials. And I'm going to estimate how long it's going to take me to run the simulation. So each one of them takes about 20 seconds. So all 5 are going to be about 105 seconds or about a minute and a half. Now this is a point where I can actually leverage parallel computation to speed up the simulations. Now to do that, I'm going to use a construct called par4, which stands for parallel for loop. Now the parallel for loop is part of the parallel computing toolbox and is going to allow me to use what are called MATLAB workers, which are essentially headless MATLAB sessions that are running in the background and are going to be carrying out all these computations simultaneously. Since each of these thermal problems is independent of each other, there's no reason why I need to do one after the other. So right now my parallel workers or my MATLAB workers are carrying out these computations. And when they finish, I'm going to have all the results stored as well as the max temperature for each of those thermal conductivities representing a different material. And also, I'm hoping that this is going to take less time than the 105 seconds that I had predicted, since I'm doing it in parallel. Now, one thing to note is that if you use par4 and you don't have the parallel computing toolbox, this code will still run. It would just run in a serial fashion. Okay, so this has finished. Now that I have all these results, I'm going to visualize them to see what the relationships are for thermal conductivities of all these materials and the max temperature. So this plot is showing me the thermal conductivity representing the 5 materials under consideration and what the max temperature was for each of those materials. Again, we see that there's a nice linear relationship here. So I'm going to use a linear model to find or to create a predictive model that is going to represent the relationship between thermal conductivity and max temperature as shown above. So I use the function fitlm and I obtain a relationship between the max temperature and thermal conductivity. The results obtained show us that max temperature is approximately equal to 331.72 plus minus 0.342 times the value of the thermal conductivity. This value is about 0.989% accurate, so this is based on the R-square value. And now let's plot this linear model to see how well this linear model adjusts to our data. So overall, we have a pretty good fit for these 5 materials that we've considered. Now, we're told that for this robotic arm, if it reaches a operating temperature of 311 Kelvin, the arm is going to shut off. So perhaps we want to design or select the material for this pivot so that the heat transfer doesn't allow for that kind of temperature to be reached. So again, let's estimate what thermal conductivity is going to be needed to reach or to not reach that 311 Kelvin temperature. So based on our model, we see that a thermal conductivity of less than 60.6 would keep our robotic arm operating under normal conditions. Any value that is larger than that is going to result in the robotic arm shutting off. So we have finished our analysis. And now if I want to share this with other people, I can certainly give this live script to other people. So if I simply save it, I can close this. And when I share it with other MATLAB users and they open it again, they'll have all the results embedded along with all the information that I have attached to it. So all of our results, all of our visualizations that we've done today are stored here. But what if I want to share this for somebody that is not using MATLAB? In that case, as we saw at the beginning of the presentation, I can tell MATLAB to export it to other environments such as PDF, HTML, or LaTeX. I'm going to generate a PDF report. I'm going to call this my thermal analysis. By simply clicking that button and generating that report, now I have a document that summarizes all the analysis that we have performed and that I can easily share with other people. So this was the first item that we mentioned at the beginning of the presentation, and we just created that report. Now let's consider a structural application. Consider a metal bracket. We would like to determine how much this bracket is going to flex or deflect if I apply a load at the tip of the bracket. With that information, we can conduct a parameter sweep to determine the most appropriate material and determine things like load deflection curves for all those materials. We would also like to create some sort of user interface that integrates all that analysis and that I can easily share with other people, even if they don't have the technical background to understand the analysis involved. So let's go to MATLAB and perform this analysis. The first part of this example can actually be found directly in the MATLAB documentation. If we go to the partial differential equation toolbox examples and look for deflection analysis of a bracket. Now that we're familiar with the overall PDE workflow, this structural problem is going to follow a similar process. First, we use the create PDE function to define a structural problem of type static solid. There are other options there, both in static, transient, and modal, to help you model the mechanics of the system you're looking to analyze, things like plane stress and strain, as well as solid. Once we've defined that model, we have to go to step 1, which is importing the geometry. Again, we have the geometry stored in a STL file called bracket with a hole. With that geometry, we once again visualize it using PDE plot. In this case, the phase F8 is where we will be applying the load. And on the phase F4, which is the back of the bracket, we're going to apply the boundary condition to keep this bracket fixed. Step 2 of the PDE workflow involves applying material properties. Now, since we're doing a structural problem, we use the structural properties function. Again, we pass the argument of our model, and we can define the relevant material properties. In this case, we're defining the Young's modulus or the elastic modulus of the material to be 200 gigapascals, Poisson's ratio to be 0.3. And if we want to account for gravitational effects, we can define the mass density as well. Another aspect of the second step of the PDE workflow involves defining boundary conditions. We use the structural BC function, the region when the boundary condition is being applied, as well as the type of boundary condition. The general idea is to specify as many boundary conditions as needed to restrain rigid body motion while accurately capturing the physics of the problem. You can model things such as constraints, enforce displacements, and for transient problems, you can define time-varying displacements. For the bracket that we're modeling, we're going to use a constraint that is of type fixed to model a cantilever type effect on this bracket. If you have a more personalized condition in your problem, you can create this type of boundary condition by writing a custom MATLAB function. Next, we define the type of loading and how the loading is going to be applied to our model. We use the function structural boundary load to define a distributed load on face 8, which is the tip of the bracket, using the option surface traction. You can define other types of loading easily for your model using things such as body loads, pressure loads, or translational stiffness. If you have any questions about any of these options, you can always search the documentation for additional assistance. For instance, we can search for structural boundary load to see that the surface traction is determined by a distributed normal or tangential force that is acting on a boundary of my geometry. Since we haven't applied any kind of meshing to our model, we can do so now using the generate mesh function and the PDE plot 3D to visualize how the mesh geometry looks. Furthermore, if you would like to verify that you have a fine enough mesh in all of your geometry, you can use the mesh quality function in the PDE toolbox to verify the shape quality of your mesh. Next, we move to the third step of the PDE workflow, which is to solve the model, visualize, and post-process results. We call the function solve and then examine the results. We've stored the output in a variable called result, and as you can see, it contains the displacement, strain, stress, as well as the von Mises stress due to the distributed load applied to the tip of the bracket. One thing that we were interested in is knowing the maximum deflection on a particular direction, in this case the C direction, which is the loading direction. So we see that we can compute the minimum by just looking at individual components of the displacement, such as the UC direction. So for the material that we're using, we get a maximum deflection of 4.5 times 10 to the negative 5 meters. If we want to visualize this displacement along with the deformations, we can use the PDE plot 3D function. We use the color map data argument and then the deflection or direction of interest. So for the X displacement, we can visualize those results and do so similarly with the Y and Z direction. Now, the last part is visualizing this deformation. So with the same function PDE plot 3D, we can have the deformation be based on a particular portion of the result. So we use the result displacement values, and we are going to use the von Mises stress as the color map to our data. So this is the result for the static analysis of the deflection of this bracket with a hole. So this was the first part of this example. On the next portion, we would like to extend this analysis to do a couple of more in-depth studies. Let me go to the second script that I have prepared for this portion. The purpose of the second part of this analysis is to perform a parameter sweep of materials in order to find a material that will result in the least amount of deflection or bending for the bracket under loading. I will also compute load deflection curves in case that we want to compare the results here with experimental values. So the first step here is just going to be loading the material properties for the 6 different materials from a file. I've assembled a table here where I can see all the properties for each of these 6 materials. I'm also going to be assembling a model for each of these materials, in this case using the create PD function structural static solid analysis. Once I have assembled all of those models, I'm going to use or leverage parallel computation to speed up my results. So I'm going to use par4 as we saw previously to assemble all of these models and then solve each of those models and then save the output to a variable called results. Now with the results at hand, I can take a look at the displacement or the deflection in the z direction to find the material that had the minimum deflection. So in this case, for all the materials we have here, our original material, which just happened to be steel, have the smallest deflection of 4.5 times 10 to the negative 5 meters. Now I'm comparing all of these values, so I'm adding this deflection value to the table of properties so I can see all of them at once. Now, what it would be a little bit easier to understand is if I can compare how these deformations look for all of the materials side to side. So let me plot all these materials and plot the deformations using a similar color scale for ease of comparison. So I'm going to create a single plot with a bunch of subplots. Let me make this a little bigger, where we can see that for each material, the amount of deflection measured on the same scale. So again, the steel has this least amount of deflection, and this material, aluminum here, we can see that has a much larger deflection. All the other materials behave fairly similarly. Now that we have computed the maximum deflection for each material and compared the deformation for all of them, let's compute the load deflection curves. I'm going to assemble a list of 10 different loads in the range 100 to 100 times 10 to the 6 and assemble a model for each of those loading conditions. So since I have 10 different loads and 6 different materials, I will be solving 60 different problems. Once again, I'm going to leverage parallel computation through part 4 to assemble all these models and find the solution, and then visualize the results as the load deflection curves. So this is the comparison of the load deflection curves for each of the 6 materials. With this, I have finished my analysis, but one thing I would like to do is be able to share this model with people that are going to be using it outside of MATLAB. So for instance, the technicians that are measuring these load deflection curves experimentally may want to use this at the lab or in the field. So how can I share this or create a user interface for other people to use? Let's see how to create user interfaces in MATLAB. If we go to the Home tab and then press on New, there's an option here to create a new app. This opens what is called App Designer. So App Designer is an app building environment, and I'm going to illustrate the process through a very simple example. On the left, I have a component library where I can add and edit all the functionality that I want to provide in users. So I'm going to add just a simple figure window here, a set of axes, and I'm going to add a way to interact with the app through a knob. So everything here can be customized. Everything has a set of properties that I can modify. So this is going to be the grid size. And the grid size, I'm going to say, well, this is going to go from 2 with a minimum value of 2 to 100. I'm going to give a title here. So this is going to be peaks resolution. Now that I have the basic layout of my app, I have to tell MATLAB what happens when the user is interacting with it. So we do this through what is called a callback. So a callback is a function that essentially gets passed whenever an event happens and executes a given command. So if I go here to callback, I'm going to add a value changing callback, meaning whenever I'm changing the values in that knob, something is going to happen. So what just happened is that MATLAB generated code automatically that manages the layout and the functioning of the app. I don't have to do any of this coding here. If I want to go back to the design view, I can switch back and forth to add or remove components. So right here, I'm in the value changing callback. And all I'm going to do is create a visualization. So I'm going to call the function serve. I'm going to place whatever results I want in the figure window that I have on my app. And I'm going to modify the function peaks with the changing value that is being entered in the knob. All right, so once I have everything, all the functionality, all the design that I want to put into the app, let's say run. This prompts me to save my app. I'm going to call it my app. Save. And as you can see, this is the app that we just designed. So right now it's not doing anything, but once I interact with it, you see that this generates this surface plot, and I can change the grid resolution of that figure. Now, let me show you an app that I built specifically for the structural example of the bracket with a hole. So this app provides a material list, or I can create my own custom material by entering the material property of the elastic modulus or Poisson's ratio. And once I've defined a material, I can ask MATLAB to find the deflection and stresses for that material. Again, this will go through the PDE workflow of loading the geometry, assembling the boundary conditions and loading conditions, meshing it, and then finding the solution. Here I can also look at the max deflection and max stress values and toggle between two visualizations. I would like to share this app with others. So let's see what options do I have there. If I go to the designer and then look at share, we can see that there's a few options here. MATLAB app puts all the required files for my app in a single installation file that I can give to others. Now there are two limiting factors here. The first one is that if I have intellectual property that I want to protect, when I share it with others, they will see all the files and functions and utilities that I've put there. The second one is if I want to share this with somebody that doesn't have a MATLAB license, then this is not going to work for them. This is where I can use MATLAB compiler to create a web app to be used in a web browser on a standalone executable. Both of these options provide royalty-free deployment and protection of your intellectual property. So let's take a look at a standalone executable. So this opens the MATLAB compiler app. Through the compiler app, I can customize my application by entering all the required information or the information that I want the users to have. So I can put my company logo, my name, and a summary and description of what the app does. So MATLAB does a dependency analysis to find all the required files to execute my application, and I can attach any additional files as well. Now I have another project that I've already created for the low deflection of the bracket. So let me open that one. And in that project, I've already entered a custom logo, all my information, and a description of what the application is doing. Now, when I package this, the end user is going to need a MATLAB runtime to run the application. Now, MATLAB runtime doesn't have any cost, and it can be attached directly to the installation or downloaded directly by the end user from our website. So once again, the runtime is just the MATLAB engine that gets installed along with the app so that when you run the application, it doesn't require to have MATLAB installed or a MATLAB license. So right now I'm going through the packaging process, and this is going to generate 3 separate folders, one of which will contain the installation file, and the other one just contains the individual files that were generated and packaged. All right, so I'm going to look at the redistribution files only, and I'm going to open the executable. All right, so it has my custom splash screen. And when the app opens, the first thing that it's going to ask me is for the material file. It's going to load the files. And once I click on find deflection, it's going to use the MATLAB runtime to go to the PDE workflow and compute the mass deflection and the von Mises stress. There are many more examples in the MATLAB documentation. For instance, let's look at modal and transient dynamics. If I go to the MATLAB documentation and scroll down through the partial differential equation toolbox, and then take a look at this examples section, then scrolling to the structural mechanics portion, I can find the structural dynamics of a tuning fork. So let's walk through this example. The purpose of this example is to compute the frequencies and mode shapes of a tuning fork and then visualize the displacement and spectrum when you hit the tuning fork, so simulate the dynamics of it. Let's go through the PDE workflow for this example. Again, we define a PDE as a structural model solid, import a geometry, and then assign material properties. We generate a mesh, and then we call the function solve by specifying the frequency range of interest. Since we're interested in frequencies very close to 0, we set up a very small value. So this will give us natural frequencies in the range of 0 to 4000 Hertz. We have to multiply by 2 pi because this is given in circular frequencies. The results show us that the first 6 modes of the tuning fork are due to rigid body motion. The 7th mode, which is at 460 Hz, provides the first flexible mode of the structure. It's usually easier to understand the results by visualizing the mode shapes of the structure. In this figure, we can see the first 6 flexible modes of the structure, where the color is indicating the magnitude of the deformation of the mode shape. Let's animate this figure. Here we can see that, for instance, the first flexible mode is only involving transverse motion along one plane, and the prongs are the only part that are having a lot of movement. Very similar to flexible mode 5, when again, only the prongs are moving, and this one, for instance, is showing a second bending mode. So the presence of these blue regions in the mode shapes are denoting the nodes of a mode, meaning regions where there is no output or no deformation or response for that particular mode. Some of the other modes are more dominated by bending or torsion or axial deformation along different planes. Lastly, let's take a look at the dynamics of the tuning fork. So for this example, we're going to define a transient problem, and the case is going to be when one strikes one of the tines of the tuning fork. So with the same properties as defined earlier, we're going to set up the boundary conditions to prevent rigid body motion by holding constraint phase 21 and 22 of the tuning fork. And then we're going to define the impulse force by simply trying to excite the first natural frequency. That is, we want to have the pressure being applied for only a fraction of the time based on the first natural frequency of the tuning fork. So we use a structural boundary load to define a short rectangular pressure pulse. We use the function structural initial condition to set zero displacement and zero velocity for the transient problem. And then we evaluate the transient model for 50 periods of the first fundamental mode. So that was around 460 Hertz. All right, now let's visualize what the time series of the vibration of the tip of the tuning fork where the load was applied. So as you can see, that is the oscillation of that tine of the tuning fork. And to make it easier to look at what the signal excitation is, we can look at this in the frequency domain using an FFT. If we look at the FFT of this, we see that we're essentially exciting mostly the first natural frequency of the tuning fork. Let's return to the presentation for some concluding remarks. In this last example, we saw how to perform structural dynamics analysis. We computed the natural frequencies and mode shapes of a tuning fork and then visualized the dynamics when the fork was being struck at one of its prongs. To conclude, we have seen how to perform FEA through an easy-to-use workflow and how to extend and perform a more in-depth analysis for applications in structural and thermal models. We use parallel computing to speed up our results and created an app that can be deployed and shared with others. These and many other MATLAB tools can help you solve your problem using a diverse set of modeling techniques. For more information, please visit our website and discovery page where you can find links to examples, code, and other webinars. I also highly recommend this webinar on engineering design and documentation, which brings additional insight into the use of finite element analysis, symbolic math toolbox, and MATLAB report generator. Thank you for your time today, and please don't hesitate to send us your comments and questions. Thank you.